Thanks very much for inviting me to discuss this paper. So let's just summarize this thing as, wait. What? Turn it on? It is on. Might not be on. No, it's on. There we go. What's the point of the paper? Let's just get to the bottom part really quickly. Regressions of investment on Q are everywhere. They're fraught with peril. They have measurement error problems, endogeneity problems. And so what these guys want to do is they want to find a better investment regression. And they want to use this as a replacement for Q regressions as a baseline. That's the goal here. And so they say, yes, we can if we just go back to theory. And the bottom line is they have a new empirical specification that soaks up more data variation than the old ones. Okay, so here's what I want to do. I want to give you a little background. I want to figure out why what they are doing works. And I give a couple of suggestions. So that's the model. So black, functions, blue, choice variables, other pretty colors, state variables. So we're going to maximize the net present value of future profits. And we are going to choose labor and capital to maximize that thing in parens, which is output minus investment costs. And we're going to maximize value, which is a function of capital, an observable state variable, and z, which is a shock to profits, which is an unobservable state variable. And then subject to this constraint. Fine. So this is a super simple model. This is what we teach all of our MBA students. Maximize the present discounted value of future profits. Okay, so how do you take this model to the data? There's basically 4 ways, and they all revolve around figuring out whether optimal decisions implied by the model look like the things that is what's going on in the data. Fine. So first thing, you can do a Q regression. And so this just says that the marginal cost of investment equals the marginal benefit of investment. And so this thing, dVdk is just marginal Q. So then if you make lots and lots of assumptions, you can get a linear regression of investment on Tobin's Q and an error. And what's nice about this is that if you make those particular assumptions, you also have to believe that the error is orthogonal to Tobin's Q. So theory actually gives you a well-specified regression. Whether you believe those assumptions or not is a different question, but that's what's going on. The other thing you can do is estimate an Euler equation. That's a different marginal this equals marginal that. It's the marginal cost of investing today equals the opportunity cost of postponing investment to tomorrow. And if you make a rational expectations assumption, then you get an error term, and you can use lagged instruments to estimate the thing. And there's no need for Q here. But you see, in both cases, theory is giving you the error. You can use simulated moments. That's just minimizing model errors, very much the same way that asset pricers minimize pricing errors. Okay, and then here's what these guys do. They're going to estimate the policy function. So what's going on here? When you get a model, when you solve it, you get a value function. That says how much is the firm worth given its state variables, given that it's this big and has that productivity shock. The policy function is a rule that says how much should I invest and how many people should I employ if I have this capital stock and get hit with that productivity shock. So they want to estimate the policy function. So I is a function of k and z. And you will notice that there's something missing in this blank spot here, which is an error term. I'll get back to that. But first I want to delve a little bit more into this. So in the model, this might be a reasonable thing to do. In the model, the state variables capture everything there is to know about the firm. So you might hope that in the data, they do a pretty good job of soaking up all the variation that there is to soak up. So it seems like a sensible thing to do. So, but it's not easy, because here's our policy function. It's a function of something that's observable, something that's not so observable. So what are they going to do? They're going to invert the production function. So here's the production function, y. It's a function of capital labor in this unobservable thing. They're going to invert it, and then take that z, stick it in up there, and then they've got something in front in terms of observables. And so that's the basic idea here. We're going to use a polynomial approximation, because we have no idea what these functional forms really are. So that's the summary of the paper. I want to understand why it's working better. And so I am going to do some exercises to try to figure out what's going on. The first will be theoretical, the second will be empirical. So is it theoretically better? So I did 3 things. First, I solved and simulated a model in which all of the assumptions for the investment regression, for the Tobin's Q investment regression, were satisfied. And I ran a regression of investment on Tobin's Q in the simulated data, did the same thing, did their state variable regression, and Tobin's Q works better. One would hope so, right? Because all of the assumptions for Tobin's Q to work are satisfied. So if those assumptions are satisfied, you would imagine that you don't even need the state variable approach. But then I did what they did. I solved and simulated a model that violates some of the assumptions. And you might imagine that these would be true in reality. Who said that all the Tobin's Q assumptions are correct, right? And so I dumped in some decreasing returns to scale, dumped in some non-convex adjustment costs, and just like they did, regressing investment on Tobin's Q gives you a much, much, much lower R-squared, just like what they found. Now this makes a lot of sense, right? So what's Tobin's Q? It's an ugly nonlinear function of a bunch of state variables. And that may or may not be what the policy function looks like. And so it appears that a simple quadratic in output and the capital stock is doing a better job of approximating the policy function than is Tobin's Q, if you have those things. But I'm not done. So what if you have a model with more state variables than just capital and this shock to profitability? Then what's going on? And this is the important thing. What if you don't include all of those state variables in the regression? This is very much what's likely to be going on in the real world, right? We don't know what all the state variables are. We're going to put in a subset of them in our regression. And what happens if we don't include all the right ones? So I stuck another one in, debt. And in this case, the R-squared from the Q regression is higher than the R-squared from the state variable regression. Why is that? That also makes a lot of sense. Tobin's Q is a function of all the state variables, and output is a function of 2 state variables. Capital is a function of itself, and so that state variable representation does not pick up as much variation. And so the answer is, theoretically, it's ambiguous. It could go one way, could go the other, depending on how much misspecification there is in the model versus what we see in the data. Fine. But nonetheless, if you look at their results, the state variable approach works better in the data. So here's what I wanted to find out. Is it just that Tobin's Q is mismeasured, but the simple model is actually a pretty good model? Or is it that the model is fairly misspecified so that a couple of state variables really work a lot better and they're all that's important? And so to do this, I got to play with a new toy, which is never a bad thing. So Tim Erickson and I did a new econometrics paper, so this is super fun. And we came up with a new estimator that gives you consistent estimates of slopes and regression R-squareds, which is what these guys are after. And the estimating equations are linear in the high-order cumulants of the data. Cumulants are functions of moments. It has a closed-form solution. It's super slick. It's really easy to use, and it has really good finite sample properties. I'm not going to tell you anymore. I don't want to bore you, but that's what I'm going to do. Okay, so here are my results. 2 columns, OLS estimates and cumulative estimates. OLS estimates, I replicate what they did. I get something that's, I cannot get their R-squareds, I can't get R-squareds that high. I have no idea what they did, but at least I get the qualitative stuff. Q regression, the OLS R-squared's lower. I do the linear state variable regression, I get a higher R-squared. I do a quadratic state variable regression, I get a slightly higher R-squared. Now let's apply the cumulative estimators, and for the Q regression, the R-squared almost, at least actually over doubles, right? So what's going on there? You have a crummy measure of Q, and that means that your explained sum of squared errors is not going to capture much variation. So you're going to get a low R-squared with OLS. If you get a consistent estimate of that R-squared, of course it will be higher. You can do the same thing to the linear state variable regression, and you get a tiny boost in R-squared, i.e. those state variables are reasonably well measured, but they're not capturing as much variation as Tobin's Q. I didn't want to do it for the quadratic. I would have had to do too much programming. Not worth it for a discussion. Okay. Now I know what's going on. I understand what's going on. Theoretically, their state variable representation may or may not be a better thing to do. what's going on in the data is that their state variables in an OLS regression are picking up more variation than a lousy Tobin's Q. If we can get consistent estimates, as if we had a good Tobin's Q, then the Q regression works better. But now I have some suggestions. So I'm going to have to disagree with Vito here. The policy function in terms of unobservables, K and Z, actually has some pretty serious endogeneity problems. And why is that? We don't know where the regression error comes from. Investment is a deterministic function of the capital and this unobservable shock. And so where does the error come from? Might come from measurement error. In that case, you have a serious error regressor correlation problem. It might come from omitted variables. Then you definitely have a serious error regression. That's also a problem. But the policy function in terms of observables, once you take Z and substitute in output, actually has more, because output and employment and debt and all of that stuff are, of course, endogenously determined with investment. So it does have some endogeneity problems, and so it's approximately on par with the Q regression there. So one thing that they want to do is to figure out how to use this regression to estimate causal effects. In other words, they want to use their regression as a baseline, and then let's say you have your favorite causal effect. You want to see whether this works and whether this baseline is a good idea. So what would you have to do this? If you wanted to use this regression as a baseline for finding a causal effect, you need to find a bunch of instruments. You have to find an instrument for this new exciting variable that you care about. But you also have to find an instrument for all the other controls in the regression because they are endogenously determined with investment. And so in this sense, you are not much better or worse off than you are with a regression of investment on Tobin's Q, except that if you want to use OLS, this soaks up more variation. But something really interesting is missing from the paper, because it's not obvious that maximizing an R squared tells us a lot about the economics of the problem. But there is something that they could do that would teach us a lot about the economics of investment. And so different model features have different implications for the shapes of policy functions, right? And so a simple estimation of a policy function can tell you an awful lot about whether these actual shapes hold. So I'll give you a quick back of the envelope example of what I'm talking about, and then I'll conclude. So here's some theoretical policy functions for different adjustment costs. And this policy function is in terms of the observables. So I've substituted Z, the unobservable shock, out and substituted back in output, just like they do, except in the theoretical model. And so we have on the horizontal axis output to capital, and on the vertical axis, which is not labeled, is investment. And yes, those numbers are real. So solid lines, smooth adjustment costs. We see a fairly flat relationship between investment and output. No adjustment costs. Of course, we see a much sharper relationship, right? Because the firm is going to respond more strongly when it doesn't have anything pinning it down. Fixed adjustment costs, we get the car-buying model. So if this shock Z is low, and therefore output is low, the firm doesn't do anything. It's only when that shock hits a threshold that it's worth it for the firm to pay the fixed cost, and then it invests a bunch, right? And that's the car-buying model. So I did a very low-tech, back-of-the-envelope estimation of a policy function. And this is not publication quality graphics, because I spent about 5 minutes on it. So what if you did a very simple nearest neighbors regression? I do have 1 minute left. So it's very simple nearest neighbors regression, output to capital and investment. I don't know, it's lumpy because I didn't smooth it very much. But you see a fairly muted response. Now, of course, this is a back of the envelope calculation. But what I think would be interesting to do is to try to figure out whether statistically that squiggly line was more closer to the flat line, the steep line, or the jagged line. I think that could tell us an awful lot more about the economics of the problem. So this is actually a new fundamental idea in the empirical investment literature. That almost never happens, so that's kind of nice. I like that. I would actually spend less time comparing Q regressions with output or cash flow regressions and spend a lot more time seeing whether these empirical policy functions could tell us more about the economics of the problem.